Okay, so now we're going to look at circuits. So actually flowing electricity, flowing electrons, or again, I like you to think about it as flowing coulombs of charge. So if you have a computer that you can use, then you can play around with this as well. I just go to whatever search, type in PhET circuit, uh, and it should be the first thing that comes up, the Circuit Construction Kit, hit play. And let's take a look at what this circuit looks like. We'll just click through on intro, and here we go. Here's what we've got. We've got the ability to put in wires, batteries, light bulbs, resistors, switches. We haven't talked about what resistors are. We haven't talked about current. We haven't talked about anything. But here I've got a battery, and I want to light this light bulb. Well, if you didn't know, in order to get a light bulb to light up, you actually need electricity to flow in one side and out the other. So the way that your light bulb is set up is there's a contact here and there's a contact here. And so as you screw it in, the electricity will flow through it from one contact to the other. Whenever I make my circuits, I tend to try to make them kind of pretty the best I can so that they're easy to follow and see what's going on. So let's just start with a light bulb. So I'm not going to connect like this, again, just because I like to try to make them pretty. They're easy to follow. I can click on this battery and I can change the amount of voltage. Now remember what voltage is. Voltage is how much energy each one of these is carrying. Okay, in reality, each one of these is an electron, but well, actually, we can pretend whatever they want, right? Maybe they're an electron, maybe they're a bunch of electrons. So let's pretend they're a bunch of electrons. Each one of those is a coulomb. If each one of those is a coulomb, and this is a 9-volt battery, then each one of those is carrying 9 joules of energy. So if I increase the voltage, I increase how much energy each one of them is carrying. You'll notice they're also going faster. We'll talk about that later, okay? But I'm changing how much energy each one of them is carrying. The more energy each one carries, the more energy it can give the light bulb, and the brighter the light bulb will be. That makes sense. Okay, so now we've got these flowing charges going around. Well, what if I wanted to add another light bulb? And let's first do this. Let's look at the brightness of this light bulb. And let's compare it to if I put 2 light bulbs in a row. So what I'm doing is I'm making it so that all of those charges have to flow through both light bulbs. You will notice actually that the light bulbs got a little bit dimmer. And if you didn't notice, let's just do it one more time. Let's add another light bulb. I think you can see right now that compared to before, those light bulbs are definitely dimmer. You might even notice that those have slowed down a little bit. Now look, still my same voltage from before. Okay, the last time that I left it at something, we can put it back down to 9 if you want. So we can see very, very dim, very, very dim, very, very dim. Versus, and I know this isn't going to be pretty, much brighter. Okay, so that makes sense. If I put up more light bulbs in, then it's going to get dimmer, right? And the way that I put those light bulbs in, I forced all of the coulombs of charge to go through each light bulb. And so if each coulomb of charge had 9 joules of energy, right now it's giving all that 9 joules to this light bulb. That's why the light bulb is so bright. But when I do this, that's not the case anymore. It can't give all 9 joules to this one because then it would have no energy to go through the rest of them. So it splits it up. It gives some to this light bulb and some to this light bulb and some to this light bulb. Sometimes it will give an equal amount of energy to both or to all 3. Sometimes it won't. It depends upon something else that we'll talk about, which is the resistance. And we'll talk about resistance in a little bit, but I just wanted you to see the way that this flows. And I want to compare that to something else. If you remember in the last video, I talked about how the voltage doesn't change when I split the path, okay? What do I mean? I am now going to give this the option of which way to go. Maybe I'll put a switch in there so that we can see. So now I've got my light bulbs, and I have this open switch. Okay, here we go. Nothing happened. Why did nothing happen? Well, this switch is open. I haven't closed or completed my circuit, and then nothing can flow. So if I close this one, there we go, it flows. Look at how bright that is. If I close this one, it flows. Look at how bright that is. Now, I'm going to close this circuit on top. I'm going to make it so that this light bulb lights up. My question to you is, will this light bulb get brighter, stay the same brightness, or get dimmer? And I'll move it here so we can easily see, right? Look at that. We can see that the brightness line is reaching all the way up here. So here I go. I'm going to close this switch. Is it going to get brighter? Is it going to get less bright, or is it going to stay the same brightness, right? Those are only three options. Nothing else can happen. Well, here we go. It stayed the same brightness. Does that make sense? You might think initially, no, it doesn't make sense. I just powered another light bulb. But what did I tell you about what voltage means? I didn't split my voltage. Each one of these things is carrying 9 joules of energy. If it decides to go this way, it's still carrying 9 joules of energy. And if it decides to go this way, it's still carrying 9 joules of energy. It doesn't matter which way it goes, it still carries the energy it had. So when it passes by that light bulb, it can still give it all of its energy. This is called a parallel circuit because, well, if it's drawn like this, these two things are parallel, but anytime the coulombs, anytime the current has a choice which way to go, it's called a parallel circuit. Earlier, when I didn't give it a choice, I put the light bulbs all in a row. It's called a series circuit because it has to go to each one of them in series. It has to go to this one, and then this one, and then this one. So this is a good visual demonstration that when I split like this, I don't change the voltage. Now let's just take this voltmeter and let's just measure the voltage on the battery. Hey, what do you know? The voltage on the battery is 9 volts. Let's measure the voltage on the light bulb. What do you know? It's 9 volts. And what do you know up here? It's going to be 9 volts. Even if I change my resistance, okay, it's still 9 volts. Now, what is resistance? Resistance is exactly what it sounds like. It's how hard it is for this to flow. Ready? Really low resistance. Look at how fast it's going. My battery caught on fire. Really high resistance. Look at how slow those are going. They are being resisted, right? Things are resisting their flow, so they're going slower. They're not resisting the flow. They're going faster. Okay, so resistance is literally a measure of how hard it is for the electrons to go through, for the coulombs to go through. We measure resistance in ohms. I'm quickly going to switch over here. Well, I'll wait a minute. We'll talk about ohms and one other thing in a second. Now, you will notice that when I apply my voltmeter, the thing that measures voltage, I take these two leads and I put them on either side of the object. I'm actually creating another path for the electricity to flow. That's actually what I'm doing. This is in parallel. This voltmeter is in parallel. What if I want to measure how much charge is flowing through? Well, I'm going to use this thing called an ammeter. It measures current, and I don't like this ammeter. Do they have the other ammeters on here? Maybe if I go to the lab. Good. So I'm going to quickly build another circuit. I'm going to build a light bulb. One. Actually, I want to switch. Switch, wire, down, over. And let's build a second light bulb up here, just like we just had. Oops, that was silly of me. Sorry, this won't be as pretty. There we go. Now it'll be pretty. Okay, so again, I'm building what I'm calling a parallel circuit. These two light bulbs are in parallel because the electricity has a choice of which way to go. Coulombs have a choice of which way to go. So currently I've got a 9-volt battery. We know, because we just looked at it, this is getting 9 volts and this is getting 9 volts. Cool. They're both getting 9 volts. This is a 10 ohm resistor and this is a 10 ohm resistor. Because they are both the same resistor, we can see, it looks like one charge goes up, one charge goes right. One charge goes up, one charge goes right. Oh, look at that. They're getting equal amounts. Let's actually measure how much they're getting. If I want to measure the charge that is flowing, I need to actually let the charge flow through this thing that is called an ammeter. It's called an ammeter because amps are the units of voltage, or sorry, of current. I don't know why I said the voltage, are the units of current. It turns out right now the current is 0.9 amps here. Let's find out what the current is up here. Well, we expect that if it's the same voltage and it's the same resistance, it's probably going to be the same current. Finally, let's find out what the current is down here. Current here is 0.9, current here is 0.9, but the current here is 1.8. Why would that be? Well, think about it. This is saying that there's 1.8 of something flowing. If there's 1.8 total, and it has to split up, then these two things are both going to get a part of that 1.8. And in fact, 0.9 and 0.9 comes out to 1.8. Let's watch what happens when I raise this resistance. Maybe I'll raise it up to 20 ohms. I raised it up to 20 ohms. This one didn't change at all. Isn't that funny? Well, it didn't change because its voltage didn't change. Its resistance didn't change. So if those two things don't change, isn't that interesting that its current didn't change? But this one's current did change because its resistance did change. And so once again, 0.45 plus 0.9 equals 1.35. And so if I go up even further, the resistance here goes up. The voltage stays the same, right? This is still a 9-volt battery. This is still getting 9 volts, and this is still getting 9 volts. This current went down. This one didn't move, and they have to add up again. Let's look very quickly at adding one more light bulb. So here we go. I'm going to add another light bulb, and I have a question for you. When I add this light bulb, I'll put a switch in so that we can start with it open and then we'll close it. And let's again measure the current through there. The current is how much stuff is flowing, and I'll go through the units of everything in a minute, but here we go. All right, I've got my 0.3 amps because that's a high resistance, so it's getting a lower current. There's more resistance to flow. This is 10 ohms, so I'm getting 0.9 amps. Hey, isn't that interesting? 10 to 30 is 3 times larger resistance. 0.3 to 0.9 is 3 times larger current. What do you know? That's very interesting. Now I'm going to close this switch. What do we think is going to happen to the brightness of both of those light bulbs? Well, if you were paying attention before, we know that the brightness will not change. We know it's not going to change because the amount of voltage doesn't change. Okay, well, what's going to happen to the current in both of those? Well, if you were paying attention, you know that the current here doesn't affect the current on these two. They're different. They're parallel. They're completely different. They don't care. They don't care that this one exists at all. What about the current down here? We know that this is 0.9 and this is 0.3, and that's not going to change. Well, when I close this, we expect some current's going to have to flow this way, right? So what should happen to the current down there? And in fact, the current down there got larger. This is a 10 ohm resistor. This is a 10 ohm resistor. So these both got 0.9 amps because they are both getting 9 volts. They're both getting 9 volts. Everything else stayed the same. But what happened? Because now there is more for this to light up, there are more paths for them to go on, the total amount of current had to increase. Less paths, smaller current, more paths, more current. Less paths, less current, more paths, more current. Seems pretty simple, right? So very quickly, I'm going to switch to recording on the board to go over just a couple of what these things are. So voltage, we already talked about. Voltage, the units for voltage are volts, which we represent with a V. So the symbol for voltage is a V. The units are volts, we represent with a V. Resistance is represented by an R. The units for resistance are called ohms, and it's like this funny horseshoe thing, okay? It's an omega. Current, we represent current with an I. The units are amps, and they're given by an A. Now we're going to go through each of those things are quickly. We've already talked about voltage. We know it is the amount of energy per charge. I'm not going to go over that. We went over it already. You can watch the other video on it if you can't remember. The units for resistance, screw it, they're ohms. We'll go over in a second what else that is, but it's just how much resistance there is to the flow of the thing. The current, well, here's how current works. I go back, I'm going to just switch back again. And I decide to go right here and I decide to count every second how many coulombs of charge go by. And as I'm counting, let's just change this. I go like, do I have a timer on here? I don't have a timer. So I start my timer. End my timer. Okay, I let 10 seconds go by. It turns out in that 10 seconds, 10 coulombs of charge went by. My current is how much charge went by in some amount of time. So in this scenario, it was, oh, I've been writing on the board and I did not switch back to the board. Sorry about that. Okay, I used a stopwatch. I found out that 10 coulombs went by in 10 seconds. So I take 10 coulombs and I divide by 10 seconds. And what do you know? I get 1 coulomb per second, which a coulomb per second is 1 amp. All right. So maybe I go back to this other one and let's change it. Let's make it a very small resistance. Here we go. And so now I start my stopwatch, go to 10 seconds. Okay, 10 seconds went by. Obviously, 10 seconds didn't really go by, but it turns out in that 10 seconds, for that resistor, in that 10 seconds, 20 coulombs went by. So that resistor ended up with 2 amps because there were 2 coulombs per second, and a coulomb per second is an amp. So how much charge goes by every second is an amp. And you might have noticed when we were doing stuff that as my resistance went up, my current went down. And as my current went up, my resistance went down, and there is this relationship. It turns out, straight from your reference table, there is this equation. And I'm going to write it every way that is applicable to you. There it is. There is a relationship between the voltage, the current, and the resistance of something. The last thing I'm going to say about this is there is a subscript that I want to put on this. And when I say that, I mean this. When I'm talking about each leg of a circuit, if I want to call this leg 1, leg 2, leg 3, and this is the total, then when I'm using these equations, I need to match stuff. If I want to know the total current, I will use the total voltage and the total resistance, okay? If I want to know through just one leg, well, the current through one leg will be the resistance through one leg and the voltage through one leg. If I care about a different leg, maybe leg 2, then I have to use all the information for leg 2. Okay, so make sure all this stuff matches. I can't use the voltage on the first resistor, but use the resistance of the second resistor. It doesn't work that way, right? Just common sense. So that's it for this. In the next video, I will go through a lot more about circuits, parallel circuits, series circuits, calculating stuff on circuits. Um, but that's it. If I can pause this.